This video is for IB 23A and B, which is on discrete random variables and discrete probability distributions. And we will start by looking at some of these definitions. So of course you can pause and write all these down. A random variable is going to be, well, it represents in number form the possible outcomes which could occur for some random experiment. So an example would be, the number of, let's see, here now I'm having trouble thinking of one. The number of geldings, well, geldings are male horses. How about the number of mares in a herd? A horse example there. And discrete versus continuous. Discrete is something that you can count. Continuous is something you measure. We've seen that over and over. And then the probability distribution is what you would do, like say, well, the number of mares in a herd, for instance, you could have 0, you could have 1, you could have 2, you could have 3, and it would just, you'd have like a list of all the different probabilities for the various numbers of X. And then a spike graph versus a probability column graph. And we'll do this for tossing 2 coins. So when you toss 2 coins, the outcomes are heads, 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 tails, tails, heads, or tails, tails, right? And so to make a spike graph with something this simple, you would put down on the bottom, you would, well, first of all, you'd have to decide what your random variable is called. So I'm going to say we have to choose a random variable. And we could say it's the number of heads, or we could say it's the number of tails. So let's just say the number of heads. So that means down here on the x-axis you'd have the number of heads. And then the number of heads, you could have 0, you could have 1, or you could have 2. So see how down on the bottom, it's not like you're listing heads, heads, tails, tails, you know, you're not listing these things down right here down on the bottom. You're listing the random variable, then the values you can have for the random variable. And then on the y-axis you would put the probability. So the probability of getting 0 heads, that could happen once. So here, let's do this. Let's make a little probability distribution. So this is the number of heads. Here there are 2, there's 1, 1, and there's 0. So that means so the probability of getting 0 heads is, right here, it happens once out of 4 times total. So that's 1/4. And then the spike graph you would just draw. Looks like this. These are a little new to me. I'm going to be honest, I've never actually used these before. So looking at the book, they have a little open circle here for some reason. I'm not sure why that is. And then the probability of getting 2 heads, that looks like herds, that could happen, oh silly me, I don't know why I put a 2 here, that should be a 1. Or wait, no, now I'm confusing myself. I'm sorry, guys. Okay, no, never mind. Okay, I'm confusing myself. I don't want to do that. The number of getting 1 head, that happens twice here. So it's going to happen a probability of a half, because there's 4 different possible outcomes, and you can get heads 2 of those. So that's going to be a half. And then 2 heads, that happens once. So that's still 1/4. And when you add all these up, you should get 1. So a 1/4 plus a half plus a 1/4 is, of course, 1. Maybe what's confusing, I bet I didn't write this probability distribution very well. No, it's good. Sorry, I'm thinking a little bit. Anyway, let's move on. And then the probability column is the same as this. It's just columns instead of spikes. So number of heads. Once you've done a spike graph, you can easily convert it to a column graph. And 1/4 and 1/2. And so you would just make, oh, I didn't draw that very well. Because what I want to do is I want to actually have, this is way too big. I want to have these spaced a little bit better. 0, 1, I'll call that 2. That way I can draw my little columns on either side. Like that. So it's like a bar graph. And then example 1. You have a supermarket that has 3 checkouts, A, B, and C, and an inspector's checking the scales to see how accurate they are. And if they are accurate, he gives a Y, he or she gives a Y, and then X is the number of accurate scales. And then we're going to list the possible outcomes. So first of all, a good way to organize this could be you could do A, B, and so A, B, and C are your 3 checkouts. And then down here you could, you're going to make the possibilities. So they could all be good. They could, let's do this. So this could be good. You're just I'm just going to randomly go through. It could be yes, yes. Whoops, that's supposed to be a no. Yes, yes, no. It could be yes, no, yes. It could be, let me think about this. Yes, yes, yes. Yes, no, yes, yes. Oh, yes, no, no. I knew there was another one. Yeah, because there should be 8. 2 times 2 times 2. There should be 8 different possibilities. So those are all the possibilities if the first one is yes. And then now there will be a no, yes, yes, no, yes, no, 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 yes, and no, no, no. So there's all 8 of them. And then over here, you're going to record the random number, which is X. It's the number of yeses, basically, the number of accurate ones. So there's 3, 2, 2, 1, 2, 1, 1, 0. Describe using X the event of there being 1 accurate scale. All this is, you might be thinking, what are they asking for? That's just that if there's 1 accurate scale, then X is going to equal 1. And if there's at least 1 accurate scale, then X could be 1 or 2 or even 3. So that's all they wanted on that one. They didn't even want us to write a probability distribution. I'm just kind of checking. Yeah, that makes sense. Okay, that's it for that one. On to 23B, which is the discrete probability distribution. So here now we're going to do the probability distributions. And rather than writing all this down again, I just copied this out of the book for you if you want to write it down, but let's just talk about it. So X is a random variable, the sample space here. So these are the possibilities for X. So back on that previous problem, it would have been 0, 1, 2, and 3. And then the corresponding probabilities are p sub 1 and so on. And then this notation right here, probability of random variable x equals x sub I. So x sub I is a particular x value. Then, p means the probability. So that means p sub I is the probability of x sub I. And as we already know, the p sub I, each probability, should be between 0 and 1, inclusive, because it could be 0 or 1. So that's what this is saying. We already know that about probabilities. We also know that if we sum all the probabilities, they should all equal 1. The sum should be 1. And if you actually list all the probabilities, that's the probability distribution. And then we go on to example 2. A magazine store recorded the number of magazines purchased by its customers in 1 week. 23% purchased 1, 38% purchased 2, and so on. What is the random variable? So if you look at this, the thing in question is how many magazines were purchased. So the random variable is X equals the number of magazines purchased. Or from the store's perspective, it's the number of magazines that they sold. Oh, that's what should be S, not a D there. Should be number of magazines sold. If you said purchased, I'm not gonna, it's the same, basically the same thing. Now we're gonna make a probability table for the random variable. So the random variable is the number of magazines sold, and the number of magazines sold, according to this data, goes from 0, or no, not even 0. They didn't even mention 0, so let's get rid of that. 1, 2, 3, 4, up to 5. And then here's your probability. And I was just going to look to see how the book wrote the notation. Yeah, they did. They write big X equals little x. Probability of, so they're using that same notation again. And then you just write those percentages as decimals. So 0.23 and so on. And then you can check by adding those all up and making sure they equal 1, which I didn't actually do, but let's see. 11, 12, 15, 20, 0, 2, 4, 7, 8, 9, 10. So yes, they add up to 1. And then letter C is to make a spike graph. Well, that's pretty easy because I have all the information right here, and this is very nice. So 1, 2, 3, 4, 5, and that's the, and do label it number of magazines, and then sold, and then here's the probabilities. And these go up to 0.38, almost up to 0.4, so I'll just count by 0.1s. And label the axes P, and then you can simply make this. So this is going to go up to 0.23, somewhere in there. 2 is up to almost up to 0.4. 3.21. 4 is 0.13. 5 is very small. Well, half of 1.1, so right there. So there's your spike graph. So it's not too bad. Kind of double checking, making sure it all looks good, and we'll move on to the next slide. Example 3. I'm trying to move this so you guys can see that better. Show that the following are probability distribution functions. So when if you look back at that back here, these are the two characteristics of a probability distribution: that each probability is less than 1, or between 0 and 1 inclusive, and that the sum of all the probabilities is 1. So we need to show both of those things when they're asking us to do this. So first we're going to find each of the probabilities. So to do that, I'm going to make a table to make it store it nicely. So here's my X, here's my probability. I'll use the book's notation. 1, 2, 3, 4. And here's a formula for the probability. So that's going to be 1 squared 2/34, which is 1 over 15, 16, 17. And then 2 would be 5/34. 3 would be 10/34. Divided by 2 is that. And 4 would be, actually, you know, I don't know that I necessarily want to divide those. 4 would be 16, 17/34. Yeah, let's not. So each one of these is less than 1. So you need to say that. Each probability. That's probably not written very nicely. You could probably say it nicely, more nicely. The probability of each X is less than or equal to 1. Actually, let's do this. I don't even like that. Let's write it with math notation. Let's make it really nice. For every X sub I is between 0 and 1. That sounds beautiful. And then we need to also sum them and make sure that the sum of the probabilities. So we could say the sum of the probabilities of X sub i's is, and we can add these up. Since these are all in terms of 34ths, you could add them. Let's see, that's going to be 27 plus 5 is 32, plus 2 is 34. So the sum is 34/34, which is 1. And now we've met both requirements, so we could say, therefore, P of X is a probability distribution. And then this one is asking for the same thing. This is supposed to be 3 choose x. Is that? Now, doesn't that look familiar? That looks like the binomial distribution, doesn't it? The general term for binomial distribution. And so again, we need to make a table with all these x's and the probabilities. So thankfully, a lot of these I can do in my head. So this is 3 choose 0. There's only one way to choose 0 things out of 3. So that's 1 times 0.6 to the 0 times 0.4 to the third. And that's going to be 1, so it's going to be 0.4 to the third. And that ends up being 0.064. Then the next one is going to be 3 choose 1. If you choose 3 things, choose 1, that's going to be 3. There's 3 ways to do that. Times 0.6 to the 1 times 0.4 to the 3 minus 1, so that's going to be to the 2. So that's basically 3. Let's multiply all that out. When I did that, I actually did that ahead of time here just to save you time. That's what I got. And then the next one is 3 choose 2. 3 choose 2. You can work that out. You could do 3 factorial over 2 factorial 1 factorial, and you'll see that that's going to equal 3 as well. So that's 3 again, times 0.6 to the 2, 0.4. Multiply all that out, and you should get 0.432. And then the last one is 3 choose 3. There's only one way to do that, so that's going to be a 1, a 0.6 to the third, and a 0.4 to the 0. And 0.6 to the third is 0.216. And then we have to sum all those. Okay, so first of all, you could notice that all the probabilities are less than 1. So you could say the x sub i's are between 1 and 0. And if you sum the probabilities, you should get 1. And I did that ahead of time, and I tried it. It does add up to 1. And then you could say, therefore, we have a probability distribution. Of course, on the IB exam, you want to write this out more as a sentence. And this is our last example. A bag contains 4 red and 2 blue marbles. 2 marbles are randomly selected without replacement. X is the number of reds selected, so that's the random variable. And we're going to make a probability distribution and a spike graph. So when I see these, choosing marbles, I automatically think of tree diagrams. So I'm going to make one. I've got a red and a blue on my first choice, and then I have a red and a blue on my second choice. So on my first choice, I have 4 out of 6 reds and 2 out of 6 blues. No replacement, so the red got chosen, so there are now 3 reds out of 5 left, and there are 2 blues out of 5 left. Down here, I chose a blue, so there are still 4 reds left out of 5, and I've chosen a blue, so there's only 1 out of 5 left. And I'm going to go ahead and I'm going to find my probabilities of each one of these myself. That's how I'm going to do this. So I've got red, red. I'm going to have the probability of red, blue, the probability of blue, red, probability of blue, blue. So red, red is 4/6 times 3/5. That's 12. I'm not going to reduce these for a reason, so it'll make it easier to add at the end. Red, blue is going to be 4/6 times 2/5. That's 8/30. Blue, red. Plus it's faster not to reduce them. And okay. The probability distribution. Oh yeah. So they're not asking us this time to show that it's that these are a probability distribution, but I do notice that these are all less than 1. And if I add them, I notice that this is 28. Oh, that's a 2. Thank goodness, because it didn't add up at first, did it? Let's get rid of that. That should be a 2. We're multiplying, not adding. Okay, great. They all add up to 1, so now I know I did it correctly. The probability distribution. So on that, we need our little table, which is going to be x, which is the number of reds. That's our x. And the number of reds could be 0, 1, or 2. And the probability that we had 0 reds, that would have been this one down here. That's 2/30. The probability we had 1 red, that happened here, plus, oh, why does that say that should be a 30? That's 8 plus 8, so that's 16/30, because it could have been either one of those. And then 2 reds is 12/30. So we could say probability of x equals x. I'm just checking to see if that's how the book did it. I want to make sure I'm doing it the way that... Oh, and this is also what they did. Well, this is what I have in my notes anyway. That's a little odd. Let me see if that's how they did it in the book. I want to just make sure I'm not misleading you at all. Oh, no, it was right the first time. Never mind, my notes are wrong. It's better the way it was. Number of reds. There we go. Okay, and then we're going to make a spike graph. That's pretty easy now. Once you have your probability distribution, the spike graph is really easy because you have all the information you need. And then you want to label this number of reds. And then your probabilities. So let's see, that's about a half. At this point, you might want to write these as decimals. Well, that's roughly a half. Did I do that ahead of time? I was going to try to save you time. I did not do that ahead of time. Oh well. This is how I did it. 8/30 and 16/30. You could get decimals. That might be easier to graph. So 0 was 2/30, so that's going to be up to about here. And then the next one was 16/30, so that's easy. I've got that on here. And then the last one's 12/30, so that's halfway between those. And there's the spike graph. You can put probability here. Great, so that's A and B. We are finished.